Yes. Hello students, welcome to the Rasaayana Institute of Sciences. So today we are going to one more topic. So as we have discussed so many topics in thermodynamics, as continuation of that, so we are going to discuss some more new topic and which will be very helpful to solve the various numerical problems in so IIT and NEET level and MCET level also, right? So the topic was heat. Heat is denoted with Q, right? So as we know that about the system, surroundings and boundary surface, then what will be the exchange of heat energy between the system and surroundings, then how heat will be defined as? It is a form of energy. It is a form of energy. It is a form of energy exchange between system and surroundings. System and surroundings due to temperature difference. What is the difference? Is means temperature difference. The energy can be exchanged between the system and surroundings, that is due to temperature difference, that is considered as heat energy. So heat is a form of energy. So it is exchanged between the system and surroundings due to temperature difference, right? So it is a disordered form of energy. Disordered form of energy. Disordered form of energy, right? So what is meant by ordered and disordered form, right? How it will be exchanged between the system and surroundings, we'll see, right? So we'll consider one system. This is the specified portion is under our observation. The remaining part is the surroundings, right? The sum of system and surroundings will be universe, right? So whenever system is there and surrounding is there, both are present in different temperatures. In first situation, the temperature of the system temperature will be very high compared to surroundings temperature. When temperature of the system will be very high compared to surroundings, at that time some amount of heat energy, is transferred to the surroundings by the system, right? So means system is evolved some amount of heat energy to the surroundings. When temperature of the system will be more, temperature will be more, that will give energy to the surroundings, means that is released some amount of energy. Therefore system released some amount of energy. System released some amount of energy. Some amount of energy, right? When system is releasing, therefore the Q will be negative sign. System is losing some amount of energy because that will be transferred to the surroundings because temperature of the system will be more, right? So the second situation, if temperature of the system will be less than of temperature of the surroundings, temperature of the system is less than of surroundings, temperature will be very high, right? Inside system temperature will be low, therefore some amount is transferred from surroundings to system. At that time the system is gaining some amount of energy. So therefore in this case system is absorbing some amount of energy. System is absorbing some amount of energy. At that time Q will be denoted with a positive sign. Q will be denoted with positive. Means when whatever is the system is going to observe some amount of heat energy, means the notation of Q will be positive sign. When system is released energy to the surroundings, means that is will be negative sign, right? Q is positive and sign terminology is very important in thermodynamics, right? Okay, so then the third condition will be there. So the third condition means the temperature of the system is equals to temperature of the surroundings, right? So here we are going to discuss about that. Energy is released to the surroundings. How much time it will be released to the surroundings, means to maintain the same temperature between the system and surroundings. That is the condition is known as equilibrium condition, to maintain same temperature. Up to there If system temperature will be very high, that will be transferred to the surroundings. If surroundings temperature will be very high compared to system, that will be gaining from the surroundings. This is the first situation. The first situation means temperature of the system will be high. At that time system is losing some amount of energy to the surroundings. In the second situation, surroundings will be very high. So at that time system is gaining some amount of energy. So therefore that will be positive. Whenever both the temperatures are same, therefore the system and surroundings are said to be present in equilibrium. So particularly that equilibrium is known as thermal equilibrium. The condition was thermal equilibrium. When the temperature of the system and surroundings will be same, so therefore system and surroundings are present in equilibrium. Such equilibrium is known as thermal equilibrium. This is about heat energy. Heat means disordered form of energy, right? So that is exchanged between the system and surroundings, that is due to temperature difference. If temperature of the system will be more, some amount of heat energy is transferred to the surroundings, that is the situation 1, right? So if temperature of the surroundings will be more, so some amount of energy is transferred to the system by the surroundings. Therefore at that time this is the situation number 2. When both the systems and surroundings temperatures will be same, therefore that is the situation is the 3rd. So therefore the system and surroundings are said to be present in thermal equilibrium, right? So therefore this is the form of energy. The units of energy will be joules, Kelvin, calories, or kilojoules or kilocalories. These all are the units of heat energy. We have to clear cut idea about that heat. What is meant by heat? Heat is a disordered form of energy. So for example, if you take some hot water in a beaker, that will be kept it on the bench, right? After some time, what do you observe? That beaker is our system. The surroundings will be surroundings to the system, right? So that heat energy of water will be transferred to the surroundings, right? So whenever temperature of the system will be more, at that time system is going to lose some amount of energy to the surroundings. Therefore that Q will be denoted with a positive sign, negative sign. So whenever temperature of the surroundings will be very high, system will be low. At that time some amount of heat energy is observed by the system from the surroundings. Therefore whenever system is gaining some amount of energy, therefore Q is equals to positive. When both the temperatures are same, that is present in equilibrium, that is known as thermal equilibrium, and the units are joule, Kelvin, calories, kilojoules and kilocalories. This is about heat energy. As we discussed that the thermodynamics explains what heat energy is transferred into various other form of energies. The other form of energies will be like work, internal energy, enthalpy, Gibbs free energy, entropy, and various forms will be there. Which will be converted into other form. So that conversion we able to get. So then before that we have to know about the work and what are the signs which are applicable for the work. The sign terminology is very important in thermodynamics, right? So we'll move on to the work, right? Right. So what is meant by work? Work is denoted with W. Work is denoted with W. It is a ordered form of energy, while heat energy is disordered form of energy, right? So coming to the point of work, that is the ordered form of energy. Ordered form of energy. It is exchanged between means that is energy exchanged between system and surroundings due to other than the temperature difference, that means particularly pressure difference we have to consider with respect to pressure. So that is called work. Only temperature difference is there, so that we may consider as heat energy. Other than the temperature difference, any other parameters may affected, so that we may consider as work, particularly in case of pressure. If the pressure difference will be there, so that we may called as work. Work is a ordered form of energy. Work is a ordered form of energy. Heat is a disordered form of energy, right? So therefore the units of work will be, it is a form of energy. That's why same units are applicable: joules, Kelvin, calories, kilojoules, then kilocalories, etc. Right? So these are the works. Even sometimes we will get the terminology pressure, volume, work also we will get in thermodynamics, right? The product of PV also will get work. So what is the mechanical work, we able to get to with the help of definition, right? So whenever the pressure difference will be there, pressure difference is there, sometimes system pressure will be more, sometimes surroundings pressure will be more, sometimes both system and surroundings have same pressure. With the help of that, so what are the notations which are applicable for the work, we'll see, right? So this is the definition of work. So as similar to the heat energy, so we will get the notations, terminology which will be applicable for the work also, right? So we have the system and the remaining part will be surroundings. System and surroundings will be there, right? So the work is the form of energy that is due to pressure difference. Remember that. So this is due to pressure difference, due to difference in pressure. So here we have system is there and surroundings are there. Therefore we will get the first situation, or that is the case 1. The pressure of the system will be very high compared to pressure of the surroundings. When pressure of the system will be more compared to surroundings, at that time the work done by the system, on what? On surroundings. Work done by the system on surroundings means system is going to do some work on the surroundings. At that time that system is losing energy. Therefore that will be denoted with W is equals to negative sign, right? So whenever the pressure of the system will be very high compared to surroundings means some pressure will be transferred from system to surroundings. Whenever pressure is transferred, there is a work done that will be by the system on the surroundings. Therefore at that time system is going to lose some amount of energy, that is W is equals to negative, right? So coming to the part of second situation, that is if surroundings pressure will be more, pressure of the system will be less than of pressure of surroundings. Now surroundings pressure will be more means some of the pressure is transferred from surroundings to system. So this is the first situation. So what about that second situation means? So the reverse, from surroundings to system. This is the second situation. At the time the arrow mark is towards the system and system is gaining some amount of energy. When system is gaining, that can be denoted with work done on the system, work done on the system by the surroundings. Whenever work done on the system by the surroundings means surroundings are going to lose some amount of energy to the system. So therefore the system is gaining some amount of energy. So therefore that is denoted with positive, right? Whenever system pressure will be high, that will donate to the surroundings. That is the situation. At that time work is negative. The terminology will be work done by the system on the surroundings. Whenever surroundings pressure will be very high compared to system is gaining some amount of energy. Therefore work done on the system by the surroundings. This time surroundings are lose some amount of energy, system is gaining, right? So if the third situation will be there, what is meant by third situation? Right. So the pressure of the system is equals to pressure of the surroundings. Pressure of the system is equals to pressure of the surroundings. Internal system pressure and surroundings pressure both are same, right? Here I am indicating the pressure of the system and pressure of the surroundings both will be same means. So that will be present in equilibrium. There is no exchange of heat. No exchange of work. There is no work done when system pressure and surrounding pressure will be same, right? So therefore there is no work done, right? There is no work done. and the system is said to be present in mechanical equilibrium. Mechanical equilibrium. When pressures are same, the system is said to be present in mechanical equilibrium. When temperatures of system and surroundings are same, the system and surroundings are said to be present in thermal equilibrium. Temperatures are remains same of system and surroundings, that is thermal equilibrium. If pressures are same, that is mechanical equilibrium. If pressure difference will be there, there is a work done. If temperature difference is there, there is a heat energy, right? So therefore 4 notations will be there: work done by the system on the surroundings, or work done on the system by the surroundings at the time W negative and positive. Then heat is observed and heat is evolved. So therefore we will get different sign terminology of heat and work. This heat and work will be correlated with the internal energy, that is called first law of thermodynamics, right? That we already discussed first law of thermodynamics in the previous lecture. So if you want, you may proceed a previous lecture, right? So these are the work and heat energy, right? So here with the help of this, I am going to conveying some conversions. So tell me which one is possible and why, right? So the first conversion, that becomes note, right? So what is meant by note means heat energy is converted to work, and work is converted to heat energy. Is it possible or not? If it is possible, why? Right? Right, both the conversions are possible. Which one? Heat is converted to work. Some amount of heat we can utilize this to do work, right? Whenever the system is going to observe some amount of heat energy, from that some of the energy is utilized to do work, right? So therefore conversion of heat energy into work is there. Somehow work will be converted into heat, right? So some little amount of heat is converted to work and work is converted to heat. Means both the statements are correct. But what was my question means? Second one. Whenever we are going to apply these conditions 100%, that means 100% heat is converted into work, or 100% work is converted into heat, right? 100% work is converted into heat, and why? This is my question. Somehow amount will be transferred, means heat will be converted into work, work will be converted into heat. But in case of 100% complete conversion, which one is possible and why? Right, so we'll see. 100% heat energy cannot be converted into work, but 100% work is converted into heat. The previous both the statements are correct. Heat is converted to work, work is converted to heat, but there is no mentioned is that completely. No, some portion, some little bit amount will be converted, right? So but in the second situation we have to go with 100%, means completion. For complete conversion of heat is converted into work means no, that is impossible. That can be explained with the help of second law of thermodynamics. So the Carnot was given that statement, no 100% efficiency heat engines are available, right? So the always it will be less than 1 only. Therefore there is no conversion of 100% heat energy into work, but 100% work we have to convert it into heat. So both in these two situations, heat 100% heat cannot be converted into work, but 100% work is converted into heat, right? So this is the difference between the work and heat, so which are correlated with internal energy. So that is called first law of thermodynamics. So that we have studied, and we'll move on to with the help of these terminologies, work and heat, we'll move on to heat capacity, right? So what is meant by heat capacity, right? So in many references books and many number of lectures, there is a statement, simply statements will be there. Even I may give the statements, but how we have to remember all those concepts with the help of this simple chart, right? So that we have to focus here. Heat capacity heat capacity is denoted with C. Right. So as like the terminology, the simple will go with the amount of heat is required to rise the temperature of any substance by 1 degree centigrade is known as heat capacity. Right. So means in a sentences form we can't remember for a long period of time. So definitely we'll go with some ideology or some diagrammatic manner or some equation manner or so any other form, either we may go through the hint, right? So definitely we'll go with either equation form or diagram form or formula. So these are the 3 key points to remember the concept easily and for a long period of time, right? So simply see, heat capacity is the amount of heat is required. So for what? For what means we have to consider the system, right? So first of all we have to consider the system, right? So this is the system is said to be in thermodynamic state, means it has some parameters. One of the parameters we have to consider, that is about temperature. The temperature is at 25 degrees centigrade. We consider a system that is present at 25 degrees centigrade. Now what I want to do means, I want to increase the temperature of that system to 26 degrees centigrade. Means how much I have to increase? 1 degree centigrade. I have to increase 1 degree centigrade. System is at 25 degrees centigrade. I want to rise 1 degree centigrade, means the system will be moved to 26 degrees centigrade. How much amount of heat energy is required? So means some amount of heat energy is required to rise the temperature of 1 degree centigrade. So that heat energy will be, Q will be known as heat capacity. That Q will be known as heat capacity, right? So simply now we'll go with the definition. The amount of heat is required to rise the temperature of any substance by 1 degree centigrade is known as heat capacity. Very simple. In this case, system is what? Any substance. System is what? Any substance. That is known as what? In case of any substance, that can be used as heat capacity C. Right? So how we'll get that will we see? Right. So we'll go with example and we'll get a equation for that. So how this will be correlated with the others, right? So that we will see, right? So example, right? So system temperature will be 25 degrees centigrade to how much? 26 degrees centigrade, right? 21 degrees centigrade to 26 degrees centigrade. So that system Q will be equals to what? C, right? So that will be Q will be equals to C. That means heat will be equals to what? Heat capacity. Heat will be equals to heat capacity. The Q is equals to C. Q is C means when 1 degree centigrade will be increases. Suppose I want to rise, right, from 25 degrees centigrade to 27 degrees centigrade. How many difference? 2 degree difference is there. For 1 degree 1 C means for 2 degree 2 into C. Therefore heat capacity is 2 into C. Right? So for example, so from 25 degrees centigrade to rise up to 30 degrees centigrade, the heat capacity is considered for only 1 degree centigrade. Here 5 times will be there. So means 25 to 26 1 degree, 26 to 27 1 degree, 27 to 28 1, 29 1, 31. Overall 5 degrees means 5 times will be there. Therefore Q will be 5 into C. Like we know the temperature, right? So some X point T1 degree centigrade to T2 degree centigrade. T1 degree centigrade, we don't know about T1 and T2. Therefore, what is the value of Q? Q is equals to C into T2 minus T1. So this can be written as Q is equals to C into dt. Therefore, from this equation, we will get C is equals to Q by dt. So this is the equation of heat capacity. Don't by heart that equation directly. See if C is equals to Q by T or C is equals to dQ by T, right? If you remember that, sometimes you forget about dt by dq or q by dt. So you may got confusion. So just you may remember the chart and we'll go with this. So definitely it will be rememberable easily. No confusion at all, right? So therefore, this is the definition of heat capacity, right? Simply again, so any substance will be there amount of heat is required to rise the temperature by 1 degree centigrade of any substance, that is known as heat capacity, and its equation will be C is equals to Q by T. C is equals to Q by T. dt means change in temperature. How much change in temperature is how much? 1 degree centigrade. So means dt is 1. Therefore when dt is 1, what about Q? Q is equals to C. That's why we wrote Q is equals to C. Means the amount of heat is equals to heat capacity. So this is about heat capacity. Right? So with the help of this, so we able to get many terminology like specific heat capacity, molar heat capacity, then heat capacity at constant volume and heat capacity at constant pressure, right? So that's C, right? So that is the equation I will be mentioned here only. C is equals to Q by dt. This is the equation, right? So what is meant by specific heat capacity? Specific heat capacity, that is denoted with C. Right? So same definition, heat capacity. Heat capacity means just you have to remember this chart. System will be there. System is consisting any substance whose temperature will be increased by 1 degree. How much amount of heat is required? That is known as heat capacity. What is meant by specific heat capacity? That is denoted by S means, right? That is denoted by S means instead of any substance, now we have to use 1 gram of substance. When 1 gram of substance will be used, that will be equals to specific heat capacity. Means we have to mention that system is particularly 1 gram of substance. Now we'll go with the definition easily. What was the definition? The amount of heat is required to rise the temperature of 1 gram of substance by 1 degree centigrade. Previously, any substance will be there. There is no particular, either that may be small or big or whatever is, right? But in this case, a specific is there. 1 gram of substance is there. So for 1 gram of substance, any substance, that is 1 gram, we have to rise the temperature 1 degree. How much amount of energy is required? That is known as specific heat capacity. Right? So in a simple form, so this is the system. So system is 1 gram of substance. 1 gram of substance. The system temperature will be increased by 1 degree centigrade. The amount of heat is required. That is known as specific heat capacity. So same diagram here repeating. Instead of that any substance, now we have to consider 1 gram of substance. That's it, right? So therefore, what is the equation derived? C is equals to Q by dt. Therefore, similarly, S is equals to Q by dt. This is for what? 1 gram of substance. If m gram of substance is there, if m gram means, so like that 1 degree centigrade and any other temperatures also will be considered. Like any other grams will be present. For example, 5 grams of substance is there. For 1 gram we have to consider, then multiplied with many number of times, right? Means we may add for each 1 gram, that will give specific heat capacity. But for m gram, what we will get means, that is S is equals to Q by m into dt. So therefore from this Q is equals to, we get S into m into dt. So this is the specific heat capacity. We will get the numerical questions based on this, right? Specific heat capacity, right? So m gram of substance is given. Specific heat capacity means, so with the help of dt is what? How S is equals to Q. How this S is equals to Q means, when S is equals to Q means m will be 1 gram, temperature difference will be 1 degree centigrade. When m is 1 gram, dt is 1 degree centigrade. At that time, the heat is equals to specific heat capacity. That is the S. So same thing, instead of 1 gram of substance, if we may use 1 mole of substance, that is give molar heat capacity. That will give molar heat capacity. Right. Very easily understand, right? So as you go through this, definitely it will be easily remember, right? So no need to read every time. For example, if you take system, right? 1 gram of, for example, if you take any one system, right? So for example, if you take one fruit, right? Whose fruit is present at room temperature. You want to increase the temperature. How much amount of heat is required? That's it, right? For example, take water. Water is at room temperature is there. Either 25 or 27 degrees centigrade is there. If it is 27, you have to increase 1 degree. How much heat is supplied to that water? So that is called heat capacity, right? So therefore, with the help of that specific heat capacity and whose equations are that, right? So then coming to the point of molar heat capacity. Instead of that, molar heat capacity, so that is also denoted with C or Cm, right? So molar heat capacity. So simple definition only, system is there. That system is particularly what? 1 mole of substance whose temperature is increased by 1 degree centigrade. Then how much amount of heat is required? That heat is known as what? That heat is known as specific heat capacity. Just only easy form to remember. So if you want to write the statements, so therefore you can write easily the amount of heat is required to rise the temperature of 1 mole of substance by 1 degree centigrade. So that is the molar heat capacity, right? So same equations also applicable, right? So that will be C is equals to Q by dt, right? Even this may be written as dq by dt also. C is equals to dq by dt. C is equals to q by t or dq by t. Here C will be moles means m. This is applicable for what? 1 mole of substance. 1 mole of substance. For n mole of substance, what we have to write? So that becomes C is equals to Q by n into dt. So this is for n mole of substance, because this is the heat capacity we have to calculate for 1 mole only. If the substance will be 5 moles of substance is there, what is its heat capacity means whether you get, so that we have to apply for 1 mole, we'll get C. So then that can be applied for 1 mole, 1 mole, 1 mole, like you have to add every time, or else simply multiplied with 5, right? So that is the equation. This is for applicable for n mole. Therefore from which Q is equals to n into Cm into dt, right? So here n is equals to number of moles. When Cm is equals to Q means where n is equals to number of moles is equals to 1 mole, right? The change of temperature will be 1 degree centigrade. So whenever these two are 1 into 1 means that C is molar heat capacity, that is equals to Q. What is that Q means? That is observed by the system. Whenever the system is going to observe some amount of heat energy, the notation was positive. System is released some amount of heat energy to the surroundings, that is called what? Negative, right? So this is the what? Molar heat capacity. You have to remember these equations. Q is equals to S into M into dt, and Q is equals to N into Cm into dt. This is Cm means molar heat capacity. If this entire process means whatever the heat is supplied to the system of 1 mole of substance to rise the temperature by 1 degree centigrade, that entire phenomenon is carried out at constant volume, that we will get this terminology of CV, means molar heat capacity at constant volume. Similarly, molar heat capacity at constant pressure, right? So with the help of same simple diagram only, we will get the entire information, right? So what was that CP and CV, we'll see. So with the help of that, we will get the relation between CP and CV also. Why we have to study CP and CV? What was the use to study? So whether gases will be there. Many gases are there. For example, noble gases will be there. The noble gases are what? Monoatomic gases. Some other gases will be there like hydrogen, oxygen, fluorine, nitrogen. Diatomic gases are there. Some gases will be there like carbon dioxide, nitrogen dioxide, right? NO2, CO2, that are triatomic gases. Other some gases will be there, methane is there, ethane is there, polyatomic gases. What is the atomicity of the gas? That can be explained with the help of consideration of the CP and CV values, right? So definitely we will get that easiest terminology with the definitions, equations, and also the atomicity of the gases also can be explained with the help of these things, right? So now we'll see molar heat capacity, right? So molar heat capacity at constant volume. CV means molar heat capacity at constant volume. Volume is constant, means same process we have to do here. So what was that process? Consider the system. Consider the system. That system is 1 mole of substance. We have to increase 1 degree centigrade. The how much amount of Q is required? This entire process is carried out. Means the heat which is carried out. This is happened at constant volume. Means we have to increase 1 degree centigrade. We have to increase 1 degree centigrade of 1 mole of substance by kept volume is constant. At that time no change of volume. Volume remains constant. By doing kept constant of volume, how much amount of heat is required? That is known as molar heat capacity at constant volume. That is the CV, right? So this is the process, same process, right? So Q is required for 1 mole by increasing 1 degree centigrade, right? So by increasing 1 degree centigrade, 1 degree centigrade will be increases, right? By increasing 1 degree centigrade, how much amount of Q is required? That is known as CV, right? So C definition equation will be there. So definitely we'll get C is equals to what? Q by T. C is equals to dQ by T or Q by dt. This can be written as dQ by dt also. This is applicable for what? Molar heat capacity. That is what? For 1 mole. If this is applied to the constant volume, that becomes getting CV. This CV is equals to means C becomes CV. When the heat capacity is considered at constant volume, C becomes CV. Therefore, this CV is equals to dQ by dt. So this dQ value is equals to internal energy. How it should be equals to internal energy, that we will see. Therefore, from which we will write that CV equation. CV is equals to change in internal energy with respect to temperature at constant volume. This is known as CV definition and equation, right? CV definition and equation. So how this dQ is equals to dE? So that we will get from the first law of thermodynamics, right? So here I want to write. Right, from first law of thermodynamics, what is meant by first law of thermodynamics? Simply dQ dE is equals to dE plus PdV. dE is equals to dQ plus W. First work will be dQ plus W is PdV. What is the W? Will discuss. Just pressure into change of volume, right? So that is displacement of an object from one place to another place. That is called mechanical work. Therefore we will get PdV only, right? So that we'll see, right? dQ dE is equals to, when volume is constant, means, as we discussed, volume is constant means the change of volume becomes 0. Therefore this entire term becomes 0. Therefore dE is equals to dQ. Therefore this dQ is equals to dE. So therefore from that we will get CV is equals to dE by dt, right? So therefore we have to write, so what was that? CV is equals to QV by dt. So from this, QV is equals to CV into dt. This QV is at constant volume, that becomes equals to dE. Therefore change in internal energy and heat is equals to CV into dt. That is the equation of CV. Right? So here we have to remember this, change in internal energy is equals to CV into dt, or that is QV at constant volume, right? So therefore similarly CP, same process that will be carried out at constant pressure. This entire process is carried out at constant pressure. So that is known as CP, right? So molar heat capacity at constant pressure, right? CP, that means molar heat capacity at constant pressure, right? So the definition also will be same. So we have to consider the system. That system is consisting 1 mole of substance. We want to rise 1 degree centigrade its temperature. How much amount of Q is required? That is known as CP. and also this entire process will be, this whatever the process we are going to do, this entire process will be at constant pressure. We have to maintain constant pressure, and we have to increase the temperature of 1 mole of substance by 1 degree centigrade. At that time, how much amount of heat is required, that is known as Cp, right? So same terminology, same notations we have to apply. So therefore C is equals to Q by dt, so that is equals to dQ by dt also. This is the heat capacity. This is applicable for what? 1 mole, right? When this C becomes Cp means this dQ by dt, that is becomes dH by dt. Means dQ is equals to dH, where H is a heat content of the system or enthalpy of the system. Enthalpy of the system. What is meant by enthalpy of the system? Here only we will get, that is the sum of internal energy and pressure volume work. H is equals to E plus PV, right? So how this dQ is equals to dH? dQ is equals to dH. Again we'll go with the first law of thermodynamics, right? From the first law of thermodynamics, dE is equals to dQ plus PdV. dQ plus PdV. dE means change in internal energy, that is E2 minus E1 is equals to dQ plus P into V2 minus V1. By interchanging this, we will get E2 plus PV2, right, minus E1 plus PV1, that is equals to dQ. E plus PV as denoted with H, therefore H2 minus H1 is equals to dQ. Therefore dH is equals to dQ. Means the heat energy is equal to enthalpy of the system, change in enthalpy of the system. Therefore as like similar to this Cv, so we have to write Cp also, right? What was that Cp means? Cp is equals to dH by dt at constant pressure, that is known as Cp, right? This is the Cp. So there is a huge information will be there, how the definition we are getting, from that how we are getting the information, right? So that is the Cp and Cv, right? Cp and Cv, and also there is a relation between the Cp and Cv. What is meant by Cp Cv relation? All you known that is Cp minus Cv is equals to R, that is R is the gas constant, that is the universal gas constant. What are the values of the R? With the units we have to remember. And as I said, the information of the Cp and Cv will give about atomicity of the gases. What is monoatomic gases, diatomic gases, triatomic and polyatomic gases, how which will be related to that. So that will be discussed in the next class, right? So don't forget to follow our YouTube channel, that is Rasaayana Institute of Sciences. So definitely we will provide some bottom to the highest level subject. So you may just follow our channel, subscribe, and you may share to your friends, definitely which will helpful to crack your examination, right? So until then, thank you.